In this video, we're going to talk about what's called the number e and the natural exponentiation function. So first I want to consider this expression 1 plus 1 over m raised to the mth power. So let's ask ourselves, what happens to this expression as m gets larger and larger? So I'm going to plug in these values of m. I'm going to first start with 10. I'm going to put a 10 right here and a 10 right there and ask myself, what do I get on my calculator? When I plug that in, I get 2.59374. And then if I make m larger, if I have m is 100, I plug that in here and there, I get 2.70481. If I plug in 1,000, I get 2.71692. Plug in 100,000, I get 2.71827. If I plug in 1,000,000, I get 2.71828. Now something interesting is happening as m gets larger. Notice that when m is 100, you have 2.7 and so on, and 1,000, 2.7 and so on. So once you're beyond 100, the first decimal place is settled, right? The first number is going to be 7 after, the first number after decimal is going to be 7. What happens if you get beyond 1,000? Well, beyond 1,000, all the values are going to be, the second decimal place is going to be 1. What happens beyond 100,000? Well, then the 8 is settled after the 1, right? And then beyond 1,000,000, 2.71828, what happens is you may have variation farther out with this decimal. This decimal goes on, and we haven't shown the other values. I'm putting a little dot, dot, dot. But we do have that the approximation is 2.71828, and it's settled at that 8. And you may have variation beyond that, but this expression, 1 plus 1 over m to the mth, it's about equal to 2.71828 when m gets large, okay? What's it exactly equal to? Well, as m gets large, we say that this expression gets closer and closer to the following number, and we write this. So parenthesis, 1 plus 1 over m raised to the mth goes to, so an arrow gets closer and closer to what we call the number e as m goes to infinity. So this is really strange, right? What is the number e? Well, it's about 2.71828, but if you want to know it more exactly, you have to take larger and larger values of m. Now you'll never truly know this. You'll never truly know e exactly. Why? Because e happens to be irrational. You can prove that mathematically. Now an irrational number, let me write that down, e is irrational. An irrational number, its decimal goes on forever and doesn't repeat. So there is no pattern that you can use to figure out what the decimal will be, as you put in infinite decimal places here. So the decimal pattern doesn't repeat. Now, what's a good approximation to e? About 2.71828. So we say that this expression goes to e. So the number that this converges to, we say in math, this converges to e as m goes to infinity. Okay, that's the definition of the number e. It's what this converges to. And e is about equal to this. This is a good approximation because we've taken m so large. So you might say, well, that's really strange. Why do we even care? Why would we define a number to be the end or what a sequence, what an expression converges to? What's the use in that? And it comes up in a couple of different ways. Let me first show you a practical application. So we know from our compound interest formula, which is this, a equals p times 1 plus r over n raised to the nt. Now p is the principal, it's what you invest. R is the interest rate, n is the number of compoundings a year. So a compounding is when you take the interest that you've made on your investment up to a certain point and you add that to your principal, so you make money for the rest of the time of the investment. You're making money based upon having a larger principal because you're adding interest to it. So if you do it twice a year, n would be 2. So if you're adding your interest to your principal twice a year, n would be 2. And if you do it monthly, n would be 12. That means you have 12 compoundings, right? Because every month you're adding whatever interest you make to your principal, and you're making interest on that larger value. Now, what if you do it daily? Well, n would be 365. Now, the question we have is, what happens if n goes to infinity? Clearly, you're expecting to make more because you're continually adding interest and making interest on a larger value. Now, what does this go to as n goes to infinity? Let's explore that. So let's first write this in the following way. A equals p multiplied by, let's write it as 1 plus r over n raised to the n over r and then raise that to the RT. Now these are the same because you can see that the R's would cancel out and you'd have what we started with. So this is simply the same as that. Now the reason I wrote it like this is because we can make a substitution. We can let m be equal to n over r, okay, and ask ourselves what happens as n goes to infinity. Well, if n goes to infinity, that means m goes to infinity because m is n over r. So as n goes to infinity, m goes to infinity. Now what happens to, if we write this using our substitution, a equals p times, let's change that to a bracket. So we've got bracket, parentheses, 1 plus, now r over n, that's the reciprocal of n over r, right? So this is an m, this is the reciprocal of m, so it's 1 over m raised to the n over r is simply equal to m, and then raised to the RT. So as n goes to infinity, m goes to infinity. Now what's happening to this as m gets large? This whole thing, right, that goes to e. That's what we talked about on the previous page, that expression goes to e. And that means this whole thing, as m goes to, or as n goes to infinity, a is heading towards p e to the RT. And this formula is the compound interest formula if you're compounding continuously. So it's called the continuous compound interest formula. So what you do is you use this if you're told that you have an investment where the interest is being compounded continuously. P stands for what you invest. E is the number on your calculator. It's about equal to 2.71828, but you use your calculator when you do this, and you raise e to the r, which is the interest rate, times t, which is the number of years. So this is what you use if you want to know the future value of an investment if you have interest compounded continuously. So that's one application of the number e. Now, e is important in a lot of other ways. In fact, if we just define a function, the basic function with a base of e, we get what's called the natural exponentiation function. Let's look at that now. So the natural exponentiation function is just the function y equals e to the x, and remember e is about equal to 2.71828. Now if you graph this function, notice that the base is larger than 1, and that means this is going to be an increasing exponential function. If we get a couple of values, if x is 0, well, e to the 0 is going to be 1, and if x is 1, well, e to the first is just e, which is 2.71828. So if you plug in 1, you get the number e. E is just a little less than 3, right? 2.71828. And the graph is an increasing exponential function. Let's go ahead and graph that in now. So there's the graph of our function. It's increasing exponentially. And one important feature of this function, actually, that you're going to talk about in calculus is that if you draw a line right here through this point, through the y-intercept, the slope of that line is equal to 1. Let's go ahead and draw that line in now. So I drew the line in through the y-intercept at 1, and the slope of that line, m, is equal to 1. And that's a fact that you're going to be talking about in calculus. In fact, that's often used to define the exponential function. So people often use that feature of the exponential function to define it, whereas in this video we defined e using the limiting value of 1 plus 1 over m to the m. Okay, let's see some other functions, or another function related to y equals e to the x, another important function. So let's graph f of x equals e to the negative x. So this would be a decreasing exponential function, as we're going to see. So we're going to graph this using transformations. We're first going to graph y equals e to the x, and then what's changed? Well, x has been replaced with negative x. So we're going to write y equals e to the negative x, where we're going to transform this graph by simply replacing x with negative x to get this graph over here. Okay, e to the x, we know what that looks like. We just talked about that a moment ago. It looks like this. Let's graph that in. So there's y equals e to the x. And what happens if you replace x with negative x? We know the effect of that transformation is to simply take the graph that you had and reflect it across the y-axis. So the graph over here is going to be simply this graph like that, which is going to be this, but simply reflected across the y-axis. Let's graph that in now. So there's the graph of our function. It's a decreasing exponential function where we simply got it by reflecting e to the x across the y-axis. Okay, so it turns out that the exponential function e to the x is one of the most important functions in mathematics, and we're going to see it quite often in calculus, so it's a good chance for us to practice using it now. Until next time.